Welcome to this lecture series in group theory. Last time we discussed the dihedral group, which was defined as follows. So first we defined Pn as this set, which is basically all these points where k varies from 0 to n minus 1, or equivalently you could say k is any integer. So what was it? For k is equal to 0, we get this point, which is basically 1 comma 0. And for k is equal to 2, k is equal to 1, we get that. Then k is equal to 2, we get that, and so on, where this angle that we have is 2 pi by n. And that is also 2 pi by n and 2 pi and so on. And we discussed this at length and saw various examples. And then we defined the dihedral group as all those orthogonal transformations which preserve this polygon. I expressed it in a slightly different way, but this is an equivalent expression of the same thing. And we saw that the dihedral group is a group of size 2n, and these are all the elements of the dihedral group, where this is the identity element, this is rotation by 2 pi by n, s is the reflection about the x-axis. Alright, I don't need any of it for today's lecture, but anyway. So these are the problems, and now let us get on with the material of this lecture. And this is going to be a very short and very simple lecture relative to what we have done previously. So what we want to do is discuss those groups which arise from fields. So first of all, suppose we have a field, let's say R. So R is a field. You can multiply things and add things, and multiplication or addition behave well with each other, and every non-zero element has an inverse, etc. So R is a field. So if you forget all about the multiplication in R, you get this object, where of course plus is a function from R cross R to R. Basically you add the two entries and report the result. And this is a group. Then, I mean, there is nothing much to say here, but let me just say that this is a group. In fact, this is an abelian group, because addition is commutative. And this is very easy to verify. 0 is the identity. Associativity is something I'm not going to check, but the identity element is 0. Because 0 plus any real number is 0 is equal to real number plus, let me not write R, let me say alpha. Alpha plus 0 for all real numbers alpha. And then inverse. So if alpha is given, then minus alpha clearly is an inverse. So minus alpha plus alpha is 0 is equal to alpha plus minus alpha. So basically inverse of everything exists, and therefore this is a group. In fact, more generally, if f is any field, then you forget about the multiplication, and this is a group for the same reason as for R. So in particular, if you take the complex numbers, then this is a group. If you take rationals, then this is a group. You take finite fields, again you get groups, etc. But we haven't discussed finite fields yet. Alright, that is one way to derive groups from fields. Another way is more interesting. So this time we consider R star. Now what is R star? R star is the set of those real numbers, again not R, let me write alpha, those real numbers which are non-zero. So another way to write the same thing is this. So this is a set, but it is a group under multiplication. So R star comma dot, let me use dot to denote the multiplication, is a group. And this is also abelian, this is commutative. So associativity again I won't check, but for identity, one is an identity of this, one is the identity of this, because 1 times alpha equals alpha times 1 equals alpha for all real numbers alpha. And inverses, one upon alpha is an inverse of alpha, is the inverse of alpha. So everything has an inverse, and the point is that 1 upon alpha is also a non-zero real number, because alpha is non-zero, 1 upon alpha is also non-zero. So I should not say all alpha in R, I should say all alpha in R star. Alright, So this is the thing, and you can do the same thing for complex numbers. Exactly the same definition. This is a group, an abelian group again, and more generally for any field, if you take those things in the field which are non-zero, then again you get a group. So the previous example was the group was arising from the addition of the field. In this case, the group is arising from the multiplication of the field. Nothing to do with addition. This is called the group of units of a field. Okay. And let me just discuss two somewhat special examples. So this is a this is a subset of real numbers. And I want to say that this is a group under multiplication. So you equip this guy with multiplication, the usual multiplication of real numbers. Then this is a group, because again, associativity is something that you can check for yourself. But identity, well, clearly 1 is the identity, and inverse, everything is its own inverse. -1 is the inverse of -1, and 1 is the inverse of 1. So this is also a group. Now, of course, it is pretty trivial for a group, but anyway, it is a group. More interestingly, we have this S1. Now, what is S1? S1 is those complex numbers which have unit magnitude. So in high school, we learn about magnitudes of complex numbers and argument of a complex number, etc. Anyway, so all the complex numbers of unit magnitude, and pictorially it basically looks like a unit circle. So this is our y-axis, this is x-axis. So this is the plane of complex numbers, and S1 is what you see here. This is S1. And this is a group under multiplication of complex numbers. Think of, in fact, not think of, everything here is already a complex number. So all I want to say is that S under multiplication of complex numbers is a group. And again, associativity is something that one does not even need to check. Identity, 1, the complex number 1 is here, and of course it lies in S1, and this is the identity of this S1. And inverses, well, if Z is in S1, if Z is a complex number of magnitude 1, then 1 upon Z is nothing but the conjugate of Z. Let me expand on that. So what am I trying to say here is that, oops, it's not working properly. Wow, wonderful. So after this long delay, what I want to say is that if Z is equal to A plus IB with mod Z equals 1, then 1 upon Z, as one can easily compute, is A minus IB. This is what I have written here in a more complex numbers like notation. This is more cogent, you could say. Anyway, so since that guy has magnitude 1, this guy also has magnitude 1, and therefore Z bar indeed lies in S1. So everything in S1 has an inverse in S1, and therefore S1 is a group. Alright, so very nice. These are some nice examples of groups. And I think this is all for this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.